Tschüss.
Okay, hi. So I'll just pick up on some things that were mentioned. So, for example, Ingo this morning mentioned a general result about cohomology, and I thought it might be good to present it in its full generality. But yeah, I actually think I've shown it last year, so I won't repeat a proof, but the good thing is you can kind of do the proof yourself if you know hot. And everything complicated you need is in the hot book, or maybe nowhere, I don't know. So there are a couple of things about iron-working plane spaces that might be, I don't know where they are, but yeah. They are quite intuitive, so it doesn't matter. So let X be a type and M and L bundles of modules, then for all short exact sequences, now in this category, which Ingo already mentioned, means pointwise short exact. So for all short exact sequences like this, there is a long exact sequence like this. So goes into the same direction, and I mean, in principle, one can also define cohomology groups for negative numbers. So in our case, if there are iron-working plane spaces, it means they are always trivial, like below 0. But yeah, and here it continues with higher indices. But I mean, otherwise it's just like repetition and so on. And you prove this using what is called the long exact sequence of homotopy groups for a fiber sequence. So you, just to give you some flavor of what goes into this. So so what you do here to form the cohomology groups is pointwise d-looping and then pi, but I mean the pointwise d-looping gives you lots of sequences, also of all the higher iron-working plane spaces, and they will all be nice fiber sequences in the homotopical sense, and that's something where you can in the end apply the fiber sequence to. Maybe you have seen this somewhere in some algebraic topology course. If you start with some fiber sequence, you can just continue taking homotopy fibers, and then you get some band of squares, and yeah, that's what's happening in the background, and it's all nice. But let's not do it here because some people have seen it anyway. Yep. Okay, but this is super useful. I mean, Ingo used it this morning, and it's also useful to calculate things about cohomology. I mean, what Ingo used is an important corollary where you only need that H1 of this one vanishes. So let's just restate this maybe. So if you know this one, then you know in this situation that the sequence on taking global sections is, yeah, I mean, Ingo wrote it with gamma. Let's write it type theoretically with pi's. So you have a short exact sequence like this. And yeah, this is super useful because it gives you existence of something. The existence, but okay. But there's another way to use this for calculations. I mean, here it's existence, but you can also calculate stuff by building a short exact sequence where something vanishes. So, yeah, this is essentially like the pattern you use in this proof, which is a generalization of what I presented on Wednesday, that H1 of an affine scheme vanishes. When you want to do Hn, you can use this long exact sequence to do some nice recursion trick, which David Wern found. So let me state what the situation is. If X is an affine scheme and M happens to be weakly quasi-coherent module bundle, and N now any natural number greater than 0, then Hnxm vanishes. And what you do for the proof is, well, first you use a construction which is quite general and appears in a lot of other places as well. And this is you first, as we did last time, you start with a cohomology class like this, and we assume eta n is greater or equal to, so last time we saw it for n equals 1. And if we take a cohomology class, we want, again, we want to show that it's trivial, which means pointwise you have this. And we have it pointwise. So we use Zariski local choice on this pointwise thing, or the connectedness of these Eilenberg-MacLane spaces. Yeah, so we get a cover of standard or basic opens which cover the space U1 to UL such that, yeah, this is trivial on UI. And what you have to imagine geometrically is that we can take this class, pull it back on something trivial, and push it forward again to have something in our original space which is trivial now. And this is like some general pattern. It's a bit already like check cohomology. So it's a bit like the check sheaf in flavor. Yeah. So what we want to do this, so I will just write down what it means sheaf-wise to go backward and forward again. So what it means is you exponentiate with the fiber of your cover in the end, and this fiber is easy to write down. So as in Hugo's talk, we think of this UI together as a cover of our affine scheme. And then the fiber of this cover is just the sigma type of all indices of these allowed ones here, such that UI of x. So this is the fiber, and this pull back, push forward construction I mentioned, it's just exponentiating with the fiber. So if I have this, then I can look at this map, which could be called diagonal map delta x, to the exponentiation. And what it does is it maps chi to 0.
Okay, I'm now going to say goodbye. Then see you.
Goodbye.
Also put your little gift in the tea kitchen.
Okay. See you. Okay. So yeah, why is it 0? Because once we are here, so chi x to be precise. So pointwise we send chi to 0. Why? Because we can construct an equality to 0, because we have the assumption that we are in some UI when we are over here. So we can use this triviality proof, this equality, to construct an actual equality of chi x embedded in here to 0. So this goes a bit towards the direction of resolutions, which you sometimes see in classical cohomology. And since this is a cover, this is also injective. Yeah. So you've seen the basic ingredients now. And yeah, so this one and the sequence over here. So let's apply it and see what it does. So yeah, right. So we take this part of, I mean, we can extend here with a co-kernel of delta at x. So we get a short exact sequence, pointwise, and we can apply the result about the long exact sequence, and then we get a sequence like this. Okay, and what does it help us? So we have our chi somewhere in here up to truncation, and if we know this gets mapped to 0, we are already done, because this is a WQC module on something affine. So it's a co-kernel of some map between WQC modules, and we know such maps are such modules are WQC again, which is non-trivial but proven. And then we know this whole thing is 0. So this is an injection. So we know if chi gets mapped to 0, it already was 0, and that's what we want to show. Picked some arbitrary cohomology class, want to show it 0. So if we know it is 0 here, yeah, so maybe a question mark here. So if we have chi equals 0 in this thing, so to write it out in maps like this, maybe some more space, or delta chi equals 0 in we are done. So we only have to show this.
I'm a little bit confused about this map delta x. You said chi x is mapped to 0, but you also said it's injective. So does this mean that chi x is 0? Or
Sorry, yeah. Yeah, sorry, that was wrong. Yeah, the point is, yeah, you're right to complain. The point is not that, but if I look at it on Einberg-MacLane spaces, yeah, thanks. Here it's 0. So, yeah. So we want it to be 0 in here. We know it is 0 here, so the difference is only this. Right? Once we have this exponentiation inside and once outside. Yeah, but you're right. Here it's injective. That wasn't a lie, and this is also non-trivial, so it has to be non-trivial as well. Yeah, and we need the injectivity to get the short exact sequence, so we can apply the long exact sequence result. Okay, so the only thing we need to make sure is that we can switch these two. And yeah, but we don't have to know that we need to switch it all the way. It's enough that from being 0 here, we can conclude being 0 here. So what we really need is it is enough to show that the map we use here to this one, the one where we make our actual computation, factors over this one through an embedding. So it's enough to be in this situation. And we do in fact know that this map factors over this one. No, I actually wanted the other way around. Yeah. Was that your comment?
Well, now we need an injection before it.
An embedding, yeah.
Yeah.
Yeah. I mean, here I really need to make sure I say embedding, yeah, because that's exactly what I need. So in hot, embedding is defined as, I have applying a function, my function, which would be an embedding, to equalities gives an equivalence. Yeah. That's certainly enough here. And yeah, so why do I get this factorization of any kind in the first place? Well, because of the universal property of this space. So it's an Einberg-MacLane space, and they have a universal property which tells me that if I find a morphism on the level of groups, then I get an induced morphism into a space. And here I know if I loop n times, I get the same space because of function extensionality. I can compute this equality in an. So, yeah. I mean, what's important to keep in mind in all of this is like pi commutes with omega, I guess. If you have pointed types, you can do this. And one application is that if you loop n times here, you get some group in the end, some zero group, and it has to be the same one on this and this side, and that's how you induce something by the identity in the end.
So is it an equivalence or is it only an embedding?
In reality, it's an equivalence.
Okay, but we don't need that.
But we don't need it, fortunately. We only need embedding at this point. And if we needed equivalence, the whole thing wouldn't work, because to show it's an embedding, we will use our induction hypothesis. Yeah. And that's the clever thing David noticed. So, I mean, at the time I had all the ingredients. I was actually aiming for something else. I was looking at check cohomology. So I had the WQC modules, like worked out to some degree for check cohomology and this long inside sequence. And I mean, this trick I had used a lot before, and yeah, but I had no idea that you can use it to prove this theorem. So that's actually something where we were at a point where we thought maybe this just doesn't work, or only for external n, and we had different methods. And then kind of fortunately David Verne joined our efforts in synthetic algebraic geometry, and then he realized you can do this trick. And I mean, yeah, why does it work? Because embedding, so this is what we need to show. So need to show, this is embedding. And yeah, it's enough to show that if you loop the whole thing, it's an equivalence. Because embedding means you're an equivalence on general equality types in the domain, but our domain is connected, so it's enough to check loops, so we can loop everything. So what we need to show follows from loop, let's write it like this, mx to eix and to loop, so the loop map being an equivalence. Since this one is connected as Einberg-MacLane spaces are. Okay. And I mean, this is exactly kmx ix n minus 1. And here you have kmx n minus 1 ix. So this again by this one. Yeah, and now we are one level down. what's the easiest way to conclude now? Yeah, okay, I mean, what's up?
No, I'm just thinking.
Ah, okay. Yeah. Yeah, so this one here is affine. It's noted. So now we can use the induction hypothesis, because what's written here is actually just a cohomology group. So, I mean, up to the set truncation. So we know it is a connected space. Connected because like H1, for example, of Ix with coefficients in Mx. No, we have n minus 1 here, yeah. So I should say n minus 1 equals 0. Yeah. And it's actually not only connected on this level, but also all lower levels. Like when I loop it, when I loop it, I can do the same thing because the index only decreases. So we actually know up to integer arithmetic, it's a n minus 2 connected space. And that means it has to be the same space as this one. Why? Because Einberg-MacLane spaces are unique. So if you know you have an n minus 2 connected space, which is n minus 1 truncated, and it's n minus 1 times loop space is the group, then you know it's this one. So then it's equiv because of uniqueness of Einberg-MacLane spaces. So it's done. Yeah.
I assume it's somewhere on the board, but why are the cohomology groups on level, or do you need n minus 1 or something, are equal? So why the n minus 1 fold loop space is on both sides the same? This is something unique, right, to conclude?
If I do here and here,
Yeah.
this is this, and I mean, when you hit 0, you have, on this side, you're just left with this group argument, and on the other side, you are left with this one, which is mx. So.
Okay, yeah, I can pull the product outside. Okay, thanks.
Yeah. So, I mean, the interesting thing is you have two of these spaces which both deloop this group, but you still don't know they are equal. And cohomology actually measures exactly this difference. Like, if they are connected enough, they are equal, but it can happen that if you exponentiate, you get more connected components, and this is actually what the cohomology groups measure. like the failure of exactness of pi also on higher deloopings for higher cohomology groups. Okay, I think that's... or do we want to push forwards? I don't know. They were used today.
So what do you want? So you can define them and then like want to prove something about them or?
Yeah, the identification of cohomology. But no, let's not do it because it's the same argument. So, yeah, it's essentially in here as well. So, yeah, okay, that's all.
All right. So we have. Thank you. Any questions?
So yes, so just about the proof, maybe an alternative way to go would be to just you want to prove by induction that this is an embedding, and that the cohomology group vanishes. So you try to prove both of them, and then you know that this map over there is an embedding by induction.
Which one?
So the second one.
Yeah.
What? This one?
Yeah, because it's the same map, but at n-1.
Not exactly the same because the cover was random, but maybe that. Anyway,
Okay, you can try to prove this for all covers.
Yeah.
I mean, actually, do you need that as a cover or just some affine? No, you only use.
I mean, for to make the argument around here work, I need it only to be affine. But to make this part of the argument work, I need a special property of trivializing the given cohomology class. Remember that in the beginning of the proof, I picked the cover depending on one cohomology class here.
In the end, we know that any affine cover would trivialize.
In the end, at some point, we know that, but not here yet. So I'm not sure at which point. Yeah.
Okay.
We know it now.
Okay. Yeah.
Okay.
Maybe it works. I'm just not sure.
Okay, so we have one last talk, which is on two categorical stuff. And now the question is whether we're going to have this talk more or less right now and have a break later, so people who need or want to leave early can do so, or whether we should have a break now.
Maybe we compromise and do a 5-minute break.
Okay, 5 minutes break and then we have 1 hour. Yeah, what is it?